Coming up on StarTalk Cosmic Queries, my friend and colleague Emily Rice is going to tell us all about the latest in brown dwarfs and exoplanets. Oh, yeah. That all comes to you from right here in my office at the Hayden Planetarium of the American Museum of Natural History. Welcome to StarTalk, your place in the universe where science and pop culture collide. StarTalk begins right now. This is StarTalk, Cosmic Queries Edition. Got Chuck Nice with me. Chuck, how you doing, man?
Hey, what's happening, Neil?
All right.
Yeah.
You know, there's a part of the universe that is a little foreign to me because most of my research back when I was like active with it was galaxies, large-scale structure, Big Bang.
All right.
And you come down, you get closer and closer and closer. There's a whole world there.
Right.
Literal and figurative world.
Okay.
People think about planets and stars being born around which you would find planets.
Right.
And we got one of the world's experts right here in the house.
Oh.
And here she goes.
Yes.
Emily Rice. Emily, friend and colleague. How you doing?
I'm very excited to be here again.
Welcome back.
Thank you.
To StarTalk. And just let the record show that whatever I'm wearing that's cosmic, and people say, oh, that's cool, that's cosmic.
Right.
I just want you to know that
Emily will come in with something cooler.
when I'm with my people, it's just camouflage.
Right.
Because everybody else has got something.
Now it is.
And you were like leader of the pack there. Aren't you involved in some haberdashery or something?
Haberdashery.
What clothing?
A little bit of this, a little bit of that.
Jewelry line?
Yeah.
Or do you still have the jewelry line?
It's a super long story, but it started as a phenomenological, like we noticed people, you were one of the originals, but other people were doing it too.
I'm an OG?
Look at that.
I think you might be one of the first. Yeah.
To be loud in my attire.
Yeah.
Yes, okay.
But a bunch of people were doing it. And so we started a blog originally, Summer Ash and I. Summer was at Columbia at the time. And we were doing our outreach stuff and wearing our stuff, like our Galaxy leggings and our NASA swag and stuff like that. We were like, this is so cool because some of the stuff we noticed was real Hubble images and stuff like that. And so we started a blog that we meant to like share it with the public. Like, oh, you bought this thing. What is it? Where did it come from? Astronomically, how it was obtained and stuff like that.
Add some science.
Add the science to it. What I didn't expect is for the rest of the astronomers to be so into it that like we presented it at a research conference, but there's always room at the research conferences for outreach and education and things like that. And the number one question we got at our poster at the research conference was, where do I buy this stuff? From the other astronomers.
Birth,
right.
Yeah.
The genesis.
Can you make stuff with my science? And at the time, we were just finding things that were out there, people's Etsy shops and small designers. Like it was kind of everywhere.
You were an aggregator at the time.
Yeah. Curator,
Cosmological Joan Rivers. Oh, who are you wearing? What galaxy is that?
Totally. But it's now become a shop. So long story short, we became an online shop. So we create our own stuff as well.
And it's
called StarTorialist.
StarTorialist.
Sartorialist.
You see what she did there?
Exactly. Yeah.
Okay, well, cool. So that's online. We can find it online.
Yeah, StarTorialist. I really thought it would be a fad that would just kind of happen and, fade away, like not be popular anymore, which, is kind of fine. But it hasn't. It's continued to grow. We've added our own stuff. So I say that we're the dark energy of the fashion universe.
Look at that.
For astronomy.
All right.
Yeah.
Dark energy is a power of expansion.
Exactly.
It accelerates the expansion of the universe.
In other words, you're unaware of why you are successful.
Absolutely. It's not fully understood. It will be. We just need a little more grant money.
Maybe. We don't know. So your expertise is newborn stars, exoplanets, brown dwarfs.
Yeah.
And I have an issue, first of all.
Uh-oh.
So when I think of a star, it's self-luminous and it's burning bright, even though burning to us means something different than to a chemist.
Radiating.
Fusing bright.
Yeah, fusing bright, but that doesn't have the alliteration and it's not as cool.
Yeah.
Right.
So stars will burn bright. Even if they're burning dimly, they still sort of luminous in the infrared or somewhere.
Yeah.
Okay. At no time am I thinking I'm looking at a brown object. So why did these objects, which are in the netherland between planets and stars,
Yes.
Because I don't call planets brown, all right, because they're going to reflect light and they're going to have whatever colors they have. And I don't call stars. Where do you get the color brown from?
The color brown apparently came from Jill Tarter, who you've had on your show before.
Yes,
so
Jill's a friend of StarTalk.
Yeah.
Active with SETI, Jill Tarter.
Yeah.
Yes,
I watched her interview on StarTalk once, and she told the story of her early career. It was actually in her PhD thesis where she did some research on these objects that were previously called black dwarfs. And so it started in the 60s.
Oh, so we had to take it away from the black. Well, that makes perfect sense.
Especially in the 60s.
Couldn't just let it be a black dwarf. Nope. No, we can't have that. Sure, a hole can be black, no problem. Yes, exactly.
We have white holes too, apparently. That's not my area of
on paper,
expertise,
but not in a real thing. Okay.
But anyway, sorry.
So the black dwarfs,
black
they were black dwarfs originally because the idea was purely theoretical, was what happens when the stars don't have enough mass pushing down from the outside to get a high enough temperature at the inside to fuse hydrogen and helium as a steady source of power. And so
which is what the sun does every day of its life.
So this is how the sun creates energy. It's a stable source of energy, of pressure pushing outwards against gravity. And the idea is that these things that started to form like stars but wouldn't have enough mass would kind of still continue to exist, but what would they look like? What would their structure be? How would they radiate? Things like that. That was first kind of described by a theoretical physicist in the 1960s. S.S. Kumar was his name. And then Jill Tarter, I think it was in 1975 in her thesis, kind of proposed the term brown dwarfs. And that kind of stuck. So she originally studied these objects. It's still at that point theoretical.
And of course, to Chuck's point, black holes were gaining very serious attention around that time.
Yeah, and so I think that's
70s.
What's like the way that we call stuff dark now.
It was a cover story of the New York Times Magazine. Black holes, what new research. So it took the word. I think you're right. Yeah.
But then they realized, like, okay, they're not fully, they're not fully unexplained. Like, they are reasonably well explained by like kind of normal physics, and so they moved away from black and just called them brown. Jill Tarter on your show said, so I started out doing this, and then I wanted to do research that mattered.
Wow.
Talking about her shift into SETI, which I'm like, I can't argue with that too much, but it
is a little bit of a diss. It is a little bit of a diss.
But it's an amazing, so she coined the phrase in 1975, and they still weren't known to exist. Like, they weren't actually discovered until the 1990s. Even then, it kind of took a while.
For context here,
right?
And I hate thinking this way, but it just jumps into my head. You realize you just described something that happened 50 years ago.
Yeah, we had a conference actually 50 years after to celebrate the original papers, 1963, 64. So that's already 10 years ago.
Had it been 1975 and we had this conversation, you'd be talking about 1925 as 50 years earlier.
That.
Wow.
That's what I'm saying. This.
Oh, God.
This, just to put that where...
Yes, put it in the proper context.
In the proper context.
You guys old.
That was not what I was trying to... Who asked you to comment?
It is amazing how far we've come and how quickly. Like, I do feel like it's not typical. Like, this is the first time in our civilization possibly that these like cutting edge research results are disseminated to the public so quickly.
Yeah. Mm-hmm.
Like, that's actually something that I love doing at StarTorialist. Like, there was the press release of the new polarized image of the black hole in the center of the Sagittarius star, the black hole at the center of the Milky Way galaxy.
Right.
And it came out, and I showed it to my students that day in class and described it to them.
Mm-hmm.
That's amazing.
Yeah. And, I can put it on a T-shirt for you and sell it at StarTorialist.
The three of us sound a little bit like we're on the porch.
Right. I remember when.
And the youngins today.
I remember we had to teletype each other and let them know about the discoveries that we made.
Teletype. We had to send a telegram.
Yes, dots and dashes is how we had to tell people about our great, significant discoveries.
Who started it?
Feels a little bit like that. So before we go on to our Q&A here, let me give you a full, dutiful introduction. You're a research associate here in our Department of Astrophysics of the American Museum of Natural History. Yeah. And you even have a desk. We get to count you as a resident research associate.
Nice.
So continued welcome.
Taking up space up here.
To those ranks. You're also associate professor of astrophysics at the Macaulay Honors College in CUNY, the City University of New York.
Yeah.
And you're in the faculty PhD program at the CUNY Grad Center. So
Yeah.
you're all in there.
It's kind of all over the place, yeah.
And
But
we
that's
see
the
some
beauty
students of yours that
CUNY.
come through here.
Yep.
It's very communal. So
I bring my
thanks for
classes here
helping.
as much as I can.
Yes.
Yeah.
Didn't I talk to your class one time? Yes.
Twice, yeah.
Yeah, thanks for bringing
You
them
happen
by.
to be here? Yeah.
I'm delighted. Just call me. And you're a founding member of BDNYC.
Yeah.
And all those letters are like in subway symbols.
Right, I was going to say, yeah. And what line is that?
Yeah. We are very proud. Oh, there's a whole story
There's just no
behind
why.
it.
There's no why.
There's no why.
There was no
Train.
Y, so we made up the Y is kind of the we made it red and white in the center. There's no Y train, but it's kind of the inverted inversion of the WNYC logo a little bit.
Gotcha.
But we had a joke going for a little while because these brown dwarfs, we have the stars that have the letters that go with them, and there's a whole story about that, right? OBAFGKM was that was kind of set into order about 100 years ago by the Harvard College computers or the Harvard Observatory women who were working as computers there. Annie Jump Cannon took that letters, and they were originally done by the strength of the hydrogen absorption line, but then they were realizing that actually it's a little bit different. It needs to be, if we order by temperature, we change up the letters, and so that's why it's not alphabetical anymore. But when we started to discover
So
these
rather than re-letter them,
Right.
Oh,
they
yeah,
kept
yeah,
it-
yeah, no,
they
we
kept them letters
They kept them
and just rearranged
and
them.
confusing people
Right.
for the century to fall.
You call it confusion. I call it job security. And there was apparently there was a bunch of different systems that they were derived, and a lot of controversy about it at the time. But since the brown dwarfs were discovered, so the M dwarfs are the coolest and the faintest stars. But for the brown dwarfs, we had to introduce new letters for the spectral type. And there are full papers going through the alphabet to say which letter should we use, basically. And so the next ones were L and T that were kind of proposed about the same time. That is like forever messed up my understanding of the alphabet because it goes ML in stars. But then the next one, when we realized, okay, there might be things fainter than these T dwarfs, cooler than these cooler than the T dwarfs. They're going to have different spectral characteristics and things like that. They proposed that there would be Y dwarfs. And so this was even in my scientific career in the last 20 years or so. And so for a little while, we had a joke with the BDNYC logo where there was no Y dwarfs yet discovered, and there was also no Y train that we would have to explain to people from outside of New York City. Then the Y dwarfs were actually discovered with the Wide Field Survey Infrared Explorer, this NASA mission in the infrared. And so now the joke has become far too long to be actually interested anymore. But we're very proud of our BDNYC logo with the subway things on there. And I feel like we've kind of
it's a
upped the
local
game.
community of people of interest, professional interest.
Yeah,
and
the
you get
three of us
together.
started at myself, Kelly Cruz, who's faculty at Hunter College in CUNY, and Jackie Faherty, who's senior scientist and
That's
educator
right
here at
here.
AMNH.
Mhm,
Yeah.
mhm.
And it was, we over 10 years ago now, something like 12, maybe 14 years ago, we founded BDNYC. And it was one of the first groups that was led by a bunch of women. It was still rare back then for kind of the three of us to be working together, leading papers together. We were counting how many papers could we find with only female authors, for example. We published one with just the three of us. We couldn't find another one that had any more.
There were not solo
That was
authors.
it.
That were more than three authors, but only women.
It sounds like that
Wow.
Bechtel test on movies.
Yeah,
Right,
it was kind
right.
of the BDNYC test or something like that.
It sounds like black people in Utah.
If you see three in one
Right.
street, there's something.
You're no longer in Utah.
It's getting better now, I feel like.
You were
It's
teleported
also-
in that
yeah,
instant. As
parallel dimension or something.
So, one last thing before we cross over. How does your interest in brown dwarfs take you to an interest in exoplanets?
Oh, they're very, very similar. So the interesting thing is that the difference in between brown dwarfs and stars is actually relatively straightforward, relatively. It's the nuclear physics on the inside. It's whether they have enough mass to create the high enough temperature at the core to fuse hydrogen and helium. That's a big difference, kind of evolutionarily and
It's a clean line,
structurally.
too.
Yeah,
Okay.
it's a very, they either turn on
So they
or they
ignited
don't.
or they didn't.
Yeah.
Okay.
But for the lower mass things, it's not as clear. And originally we had we wanted to have a similar definition. And so there was this lower mass demarcation that was 13 Jupiter masses instead of between the stars and the brown dwarfs, it's about 75 Jupiter masses. And that was, again, derived in like the 1960s. For the 13 Jupiter masses, we wanted to make this nice clean break between the brown dwarfs and the planets. And so 13 Jupiter masses is the mass.
Just to be clear what you're doing, you've turned Jupiter into its own
measurement.
Into its own
measurement.
measurement.
Yeah, we always.
Right.
Oh, yeah.
I don't
with
know,
the masses.
I
Yeah.
don't know how common an exercise that is in the rest of society. Okay? So, but yes.
In New York City, I don't know. Yeah, it's one block, but it's one avenue block versus one, street block or something like that.
Mm-hmm.
It's whatever miles. But yeah, we do this in astronomy all the time. This is the great, astronomers, we say astrophysicist if we want people to be impressed or something like that. We'll take anything and call it one or set it relative to one another to make the math easier. We'll do anything to make the math easier.
Earth-sun distance,
my goodness.
just one astronomical unit.
Well,
this is
there
one.
you go, one.
And how far away is it from the sun? Is 10 of us.
Right.
Or 5 of us, right.
Yeah.
Right.
Yeah. So the 13 Jupiter masses, above that, there would be some nuclear fusion going on. So more massive than that, you might fuse a little bit of hydrogen, a little bit of lithium, because that's easier to fuse. Deuterium, which is heavy hydrogen, is also easier to fuse. And so that easier means it will fuse at lower temperatures. And so above 13 Jupiter masses, there might be a little bit of fusion going on. And then below 13 Jupiter masses, they figured out there's no fusion going to happen ever. But the thing is that this demarcation doesn't actually make a huge difference in the long term for these things. Not in terms of the structure, not in terms of the evolution.
So how does it get you interested in exoplanets?
Yeah. So the what ends up happening is that the brown dwarfs are actually really similar to the massive exoplanets. And some of these massive exoplanets are things that we found more easily than we found the Earth-like exoplanets.
So the size of your party grew.
Yeah. 5-10 times the mass of Jupiter. We found those exoplanets around other stars even more easily.
So you find yourself at the same conferences as these other...
At first, we used to have we called them cool stars conferences, and first the brown dwarf people went to the cool stars conferences, but then when the exoplanets got big enough, now there's a ton of different exoplanet conferences that the brown dwarf people go to. We kind of go to both too.
Yeah.
And we bring our karaoke along, but it's kind of like...
And it's also where collaborations are born. I mean, it's
especially
you can't undervalue.
And then the planetary science people who have studied the planets in the solar system for so long are like, what are you guys doing? Because so much of it, needs, Jupiter we know in a lot more detail, but there's still a lot of open questions. Saturn we know in a lot more detail. Even Earth atmosphere stuff, brown dwarf people can learn in order to study these things.
Mm-hmm.
Yeah.
All right.
Hi, I'm Ernie Carducci from Columbus, Ohio. I'm here with my son Ernie because we listen to StarTalk every night and support StarTalk on Patreon.
This is StarTalk with Neil deGrasse Tyson.
Let's jump right in.
Okay, we got questions.
Let's do it.
And they are all from our Patreon people, and they are all for you specifically. All right, so this is from Laura Fortier. Says, greetings from Arizona. Hello, doctors Rice and Tyson, Lord Nice. I have heard that brown dwarfs and hot Jupiters are similar. In what ways do they differ? And how are they made when they are clearly separated from a solar system? I heard somewhere that we don't really know how low-density stars are even created. Have we learned more?
People doing their homework before they come in on
Yeah, they really are.
So the hot Jupiters are one of these things that we found around other stars that we haven't found in our solar system. And the hot Jupiter is a nice one because it is what it sounds like. It's a Jupiter-sized planet, Jupiter mass planet.
That all the other planets think are super sexy.
Hot planets, right?
Oh, hot Jupiter in the house. Okay, go ahead.
Close to its star so that it's irradiated by the star.
So it's not hot on its
close.
own.
That's the thing, is it's not hot on its own. Yeah.
Oh, so that's a little
It gets hot from the
circumstantial.
star. Yeah. And so that's the interesting thing is that these hot Jupiters end up being similar to mass and maybe a similar temperature to a brown dwarf, but for a different reason.
For a different reason.
Yeah.
Look at that.
Like whether the radiation is coming from the outside or the inside. And so there's similarities, but there's also differences. Yeah. So those are one kind of
Thanks
overlap.
for clarifying that. And what's the other part of that question?
She said, I heard somewhere we don't really know how low-density stars are created.
Yeah.
Okay.
So
did they mean low mass stars? What in low density?
Yeah, they can be kind of the same. The interesting thing is that because of the physics going on at the very, very cores, these things kind of plateau in size, and so they do get lower and lower density.
Okay.
Because the mass decreases while the physical size stays the same. And so they do get lower and lower density, but we talk about them more in terms of their mass. We don't fully know like how many of the low mass ones are out there. That's just like counting them. We don't fully know that. We don't really know how they formed or how low the mass can go when it forms like a star does.
But why did we invite you to this? We don't know. We don't know.
Security. Yeah.
So let's get to brass tacks. I have a gas cloud out there. There's so many beautiful images of gas clouds.
Yeah.
From Hubble, from especially
WST, beautiful ones. Yeah.
So, and we see stars being born. Why weren't those stars born a billion years ago? Why are they being born now? What happened in that gas cloud ever at any time to make a star?
Oh, it depends on what the
And how does it know to make a high mass star or a low mass star?
Yeah, the universe just does that. Like we don't necessarily,
Now, why'd she get away with that answer?
I was about to say, she actually gave you your answer, but much more succinctly, which is the universe is under no obligation to make sense to you.
That's true, yeah. That's kind of figuring it out and seeing if there's a law. So there does seem to be a law.
We should allow that in the PhD defense, the thesis defense.
Right.
So, excuse me, why do you get this? The universe just does that.
Right, exactly.
So I feel like that is like as soon as you can say like confidently, I have no idea or I don't know or I don't think we can know, like that's when you're an actual scientist.
Yeah, very
like
good.
there's a lot of pressure to know the answer.
Very important philosophical point.
The confidence and the uncertainty like makes the scientist.
Because everybody else is trying to give an answer.
I was going to say, that is the difference between like, I hate to bring
somebody
it up, but
BSing
science
you.
and religion. And you said somebody BSing you.
Yeah, I
said
think so,
science and religion. But yeah.
Oh,
is that
I didn't mean to conflate those two, but...
But no, it's the truth. Like, religion has an answer for everything.
Basically,
they have an answer.
Even when one answer contradicts the other answer.
It doesn't make a difference. I gave you an answer.
Yeah.
That's very cool. Or I should say maybe it's like my parents, which were because I said so.
Yeah, exactly.
That's the ultimate
That's the
answer
ultimate
to
answer because I said so. That's very cool. All right. Well, this is great. That was great. That was really informative. Thank you very much, Laura.
And say her last name one more time.
Fortier.
Fortier.
Yes, which is not my forte to pronounce Fortier.
Nice.
Okay, this is Jason Dorkson. And Jason says, what is the largest dwarf star ever discovered? Oh, look at that. He's going for the jumbo shrimp angle. He's going for the jumbo shrimp angle. What is the largest dwarf star that we have actually seen?
That's a good question. I don't think I can answer that very concretely. And the reason why is because there's more weirdness here that I haven't even really touched upon, which is the fact that when the stars are formed, they kind of form and they start to fuse their hydrogen and helium, and they kind of, once they turn on, they stay that way for a while. They get stable. Right. And so they have the same temperature, the same luminosity, the same mass for a long time. That's the other thing is
the same mass except for the little bit they're losing when they convert it into energy.
Oh, yeah, but it's a tiny, even for the small stars, it's a tiny bit of mass.
Tiny fraction of the
tiny
total.
fraction of mass. Even for the big stars, the mass doesn't change a huge amount with the nuclear fusion. But the big stars have shorter lifetimes, and the small stars have longer lifetimes.
Yeah.
So the low mass ones?
The low mass ones, we think they can last, and I can't believe we can throw around this number, but for like 1 trillion years.
Yeah.
Mm-hmm.
Well,
they're
you
not
can
going
throw it around
anywhere.
because nobody understands what it
Yes,
is.
and probably nobody's going to be around to prove me wrong.
Way longer than the universe has been alive to this day. Right.
Yeah.
Wow.
Right.
Look at that.
But the tricky thing is, so that star becomes stable and kind of doesn't stay, but the brown dwarfs will kind of gradually cool and fade over time.
Okay.
Like they have this kind of residual heat left over from forming, but then they just kind of cool and fade. And so as astronomers looking at them, we can't really tell whether we have a young, low-mass brown dwarf that's just formed or an old, high-mass brown dwarf that's been cooling off for a while.
Because they last for so long, you can't really tell. They look the same.
The stars last for a long, long time, but the brown dwarfs cool off.
Right.
Yeah, and so we have this, we call it the age-mass degeneracy. So we don't know if we have a young, low mass thing that's
Right.
just hot because it's still young,
Right.
or an old high mass thing that's hot because it's a little bit higher mass, but it's been around for longer
long
because
time.
they're
Right,
cooling
check.
off
Right.
with time.
We have to get her to explain degeneracy. There's an English
Degeneracy, yeah. It's
Yeah.
like where you can, degeneracy is you can't tell the
That's a
difference.
lecherous brown dwarf.
I know, there's
Yes,
degenerates.
it has a gambling problem.
No, the brown dwarfs of today,
Oh,
they
God.
just are not what they...
It's just not what they used to be. Oh.
I'm never going to be able to explain my research again. It's so fun. We get so used to using these terms
Right,
and
so,
don't think
so
about
degeneracy
the other. Yeah.
is a mathematical...
a physical term
physical
for us.
mathematical...
Yeah.
So give it a
Yeah,
gander here.
there's a couple different kinds even. So our degeneracy, the age mass degeneracy, is that you don't know one without constraining the other. So it's ambiguity is the colloquial, like that's the
Two things look alike,
Right.
but
we
they
can't
can
tell
be
the
very
difference.
different from each other and are just happen to look alike in that moment.
Right.
Yeah.
And you can't distinguish one from the other
Yeah.
without another dimension
way
of
to
data.
measure. Yeah, we have to be able to measure the mass somehow, or we
You
have
need
to be able to measure
another
age
data point
somehow.
to
Yeah, which we can't
break
really
the
do.
degeneracy.
Gotcha.
And there's another degeneracy.
Yeah, and then the other degeneracy is like the cores of the objects are partially degenerate, we say, and that's like a quantum mechanical thing, where the actual electrons in the atoms get so close together that they fill up the quantum states, and that provides pressure against the mass pushing
Can't
down.
keep squeezing down.
Wow.
Yeah.
Look at
Yeah,
that.
so that's called
like-
degeneracy pressure.
Yeah.
Okay.
So I've forgotten we have degeneracy used in two completely
Yeah,
different ways.
they are two different. I
Right.
never thought about that before either.
Yeah.
It's such
Okay.
a weird. We
Yeah.
speak our own language
Yeah,
sometimes. Yeah. And so this high mass, so it's really hard to tell actually exactly how high mass something is. Like nominally we have the 75 Jupiter mass cutoff,
Right.
but we also don't know is it young or
Yeah.
is it old or
Right.
something like that?
Which
Yeah.
will factor into
Yeah.
whether or not it is or it isn't, which factors into whether it's the largest brown dwarf we've ever seen.
Yeah.
I got you.
Yeah.
Wow. You put all the, damn, that's
It's-
rough.
It's weird.
Science is hard.
That's
Yeah.
rough, man.
Science is hard.
Yeah.
You don't just look through a telescope. Here's the answer to that question.
Yeah.
Yeah.
No, it's
You
like,
find new problems as
Yeah.
soon as you
Right.
dig a little bit deeper.
So,
Yeah.
Jason, the answer to your question is we don't know. We don't know, man. I'm sorry.
How many is that? I think that's, I don't know
Yeah,
for the
you're
first
up to
two
like
questions
5 here.
so far. Yeah.
All right.
That's pretty cool, though. I love it.
But who is it that says the only thing I know is that I know nothing? What's that quote
All
from?
I know is that I don't know nothing. That's Operation Ivy, but
No, I think before that, I'm thinking ancient Greece, Socrates.
Socrates and Operation Ivy.
So it'd be Socrates, actually.
So Grace Johnson.
Socrates, it was, if I know anything at all, is that I know nothing. So
Right.
I'm paraphrasing.
So yeah.
All right, this is Nobble Gobble. And Nobble Gobble says, salutations, doctors and Lord. My name is Caleb Noah Gettin. Okay, Noah Gettin. Noetkin. There you go. My name is Caleb Noetkin. And thanks, Caleb. He says, good luck with that one, Chuck.
Even knows.
Son of a gun.
He knows.
I can't believe you, man. Then he says, this is Caleb from Wichita,
People are cold.
Kansas.
People I get no respect.
They're just letting the cat mash on the keyboard that Chuck is going to have fun with this one.
Yeah, tell me about it. He says, since brown dwarfs are sort of an intermediate object between
Yeah.
a planet and a star, I was wondering if there was a common trend between mass composition and magnetic field strength.
Oh, gosh. Magnetic
Wow.
field.
Look at that.
This is one of those things where if you want to trip up an astronomer, you ask them about dust or you ask them about magnetic fields.
Right.
And it's nice because it's nice because it applies really across any kind of research. We try to ignore it because those things complicate things hugely. So yeah, these things do have magnetic fields, but we actually don't know how the magnetic fields are generated on these stars. We
Oh.
think we know how magnetic fields are generated on the sun because there's this cool thing called the tachocline, and it's like these moving charges are going to generate the magnetic field, and we think that's where it comes from on the sun. And that tachocline is a border between a radiative zone and a convective zone.
Okay.
So there's energy transport is happening in different ways. But for brown dwarfs, what we think we understand of the structure, and this is all from modeling things and understanding how energy transport is supposed to happen, we think at some point they become fully convective.
Okay.
So this is kind of cool. It's like the convection is this big bulk motion of material that happens when you like boil water and stuff like
Right.
that. So it's relatively
It's
familiar
like an
to us.
internal churning?
Yeah, it's
an
this
internal
churning. But instead of the churning only going down part of the way inside the stars, which it does
Right.
for the higher mass stars, it goes all the way down.
So the two of those together, you have a radiative effect, which is the outward pushing of the star, and then you have the internal churning, and the two of them together, like the Earth's core rolling around inside of us, makes a magnetic field. Is that?
Well, we don't know for the brown
we-
dwarf. That's
oh.
the thing, is that because
I'm trying to figure it out.
We
all I know
don't
is they're up
know.
to 7 I don't knows.
Yeah. So we also think the magnetic fields are going to be different across the different types
So
of brown
why did you call it a
dwarfs.
something
Yeah.
Klein and not
A tachocline.
tachocline and not just a
Tachyocline.
dynamo? Or is a dynamo the broader term?
Dynamo is the broader term that generates the magnetic fields. Yeah. Am I messing up my solar physics? Hopefully not. I could be. Somebody can get their 5 cents back.
Right.
Their $5 back.
So what is the difference between that and a star? Because we know that's what had happened, like in our own sun.
Yeah, in our own
What-
sun, we've kind of got these bigger motions. In the brown dwarfs, we don't know fully where there isn't this separation between the inner layers, and so we don't know where the brown dwarf, where the magnetic field comes from. But there
Gotcha.
is a magnetic
But there
field. We
is
see
a magnetic
spots
field.
on the low mass stars and on the brown dwarfs. We see aurorae
Spots is good evidence of
on
a
the brown
magnetic
dwarfs.
field.
Yeah, both of those
on the
things.
sun, spots always come in pairs.
Right.
And one is plus and one is minus.
Oh, I did not know that.
Yes, it's a cool fact.
There's
That's really
a bright
cool.
spot that goes along with the dark spot. Yeah, I think the bright spot is harder to see usually.
Look at that.
Yeah,
That is the first I've ever heard of that.
Yeah.
That's
yeah.
well,
And the solar wind that we're going to
Here's something else I heard, which is consistent with what you just said. Back in my day, you would accuse someone of, if they're presenting their research, and they say, the bigger is the effect of a magnetic field in what they describe, the less they know about the subject.
So, yeah.
The less they can explain, they put in more magnetic,
magnetic
field, which is
field.
what accounts for everything that
Right.
they don't otherwise know.
Yeah. It's magnetic fields are challenging. They're very hard to understand.
Oh, wow.
Yeah.
That's really, well, that's,
Astrophysically, in a lab, we got it.
Right,
But
yeah.
yeah.
yeah, if we're talking magnets, it's no big deal. But yeah. Wow. Well, Caleb, that was a great question, man.
3 I don't know. We're up to
It doesn't make a difference. Here's what
I was counting 7, but if it's only 3, good. All right.
But this is what I'm loving about the I don't knows. Every time we don't know something, I learn something.
Yeah.
Like something else comes out of it that I've
Yeah.
never heard before.
Yeah.
Yeah.
That's the third time that we've had an I don't know. But every single time there's something really cool
Yeah.
that we find out in place of I don't know.
And by the way, it's also a measure that the field is very much embedded in its own frontier.
Right.
When you're on a frontier, every step you take is into the unknown. Yeah.
Okay, this is Atticus Thompson. Atticus says, hello, Dr. Tyson, Dr.
But
Rice.
is this a letter from the Civil War? We need that voice.
My dearest Dr. Tyson and Dr. Rice, today was an especially difficult day.
Signed, Atticus. Is anybody named Atticus today?
Yeah,
no.
they're all in Brooklyn.
Oh, is that right? Oh, it's a thing.
100%. They're all at the
They're
playgrounds
all-
in Brooklyn right now. I
And
guarantee
you are so
you.
right.
Wow.
But that's Atticus from Atticus Finch.
Quite possibly.
Yeah,
Yeah.
Okay.
I would think. But anyway, he says, my name is Atticus, and I'm 9 years old.
He's 9. Okay.
He says, I live in Soddy Daisy, Tennessee.
All right.
I want to know if two brown dwarfs collided, do they become a larger brown dwarf, or would they just become a low mass star?
Ooh,
That is
I
a very good
love
question.
that.
Yeah.
Okay, so Atticus, first of all, you ain't fooling nobody. I don't care if you're 9 or not. I know your father helped you with this question.
What are you talking about?
You're not fooling anybody, Atticus. I'm Atticus, and I'm 9 years old. I would like to know.
Wait, dude, when I was 9, I could have asked that.
You could ask that question? Okay.
Oh, yeah.
See, yeah.
That's when
I was going to say, you're going to work
interest-
for Atticus someday.
My interest in the universe was birthed when I turned 9 years old.
Okay.
Oh,
yeah.
All right. Well, Atticus, I take it back. No, I don't.
No. You want to get at him? Ask him if he paid the $5.
Yeah, but if he's asking questions like that, he might have a job. I'm just saying.
Okay, so what happens when stars collide?
Yeah, well, it's going to depend on their mass.
Really?
Yeah, it's not outside the realm of possibility if you have that's just a multiplication or an addition problem, really. If the two brown dwarfs come together and have more than that 75 masses.
Jupiter mass.
In
Jupiter?
theory, yeah, it could ignite hydrogen fusion.
Right.
Wait, so the whole star will reorganize.
Right.
Quite possible.
Possibly.
It's something that we don't like expect it to happen a lot. I don't.
It wouldn't be an
think,
object
like,
with two separate cores, we don't think, because gravity and
they would
friction
kind of
would
like
bring it
as
together.
they get closer together, they would get like torn apart a
Right.
little bit, and so it
And then
would
kind of-
probably like if they did
And
coalesce.
And then coalesce again.
Yeah, we know this happens for like the higher mass stars because
Okay.
we see that black hole mergers are what trigger the gravitational waves. We have stellar mergers, like it creates more energy, and so we have more evidence of it for the high mass stars. So we don't really think about it too much for the low mass stars because I think we don't have a lot of super close binaries. Like there's not going to be a huge amount of energy loss. Like you're going to need some kind of energy loss to get them to get closer and
Come
closer
together.
to one
Something
another.
has to eat the energy of their orbit.
Right.
Their
Yeah,
orbital
if
energy.
they're going to come
Otherwise,
together.
that's why we don't just collide into the sun
Yeah,
right now.
It's a very slow process for any kind of orbital change like that.
So and
But if it did happen,
and blue stragglers are similar.
yeah, that's how
objects.
these weird stars
Yeah.
Wait,
kind
what's
of.
a blue straggler?
You know about the blue
That's-
stragglers?
No.
Yeah.
Tell me. Because
Yeah. So you look at
I know
a
it's a
cluster
thing.
of stars,
Right.
all born together. So they all
Okay.
should be evolving together as we
Right.
understand stellar evolution. And then there's some stars that are like hotter and bluer than anybody else is. And it was a big, in my day, it was a big mystery until someone said maybe these are two stars that have merged. And when you
oh.
merge,
they've become
you get
hot
to
again.
you get to re-energize your core with
Gotcha.
fresh material,
Right.
so that you will have a prolonged life expectancy and you'll come out a little hotter than you're otherwise supposed to
They're
be.
the late bloomers of the stellar nursery.
Well, they got an injection
Look at
of
that.
new
Had a
Yeah,
growth
yeah, yeah.
spurt over the summer.
blood.
Look at me.
Yeah, so they stand out from all the rest of the stars.
Oh,
Yeah,
wow.
blue stragglers, because everyone else has evolved
Right.
together.
Yeah, because they all were born together.
They were
so-
born together, and
Right.
this one got an extra
And
infusion.
the high mass ones, especially, are bluer to begin with and shouldn't live as long.
Right.
Yeah.
Right, and so these are
Interesting.
standouts. So I never
Yeah.
thought about the brown dwarf. You can ignite a brown dwarf that otherwise would have had to live its life.
Yeah, in theory, I think. In practice, I don't think we see it a lot. We do see, it's,
Maybe
it's
they're
hard to
just
tell whether or not
stars.
things are binaries. Yeah, maybe they just turned into these stars.
Could be.
Maybe they're just a star you're ignoring over on the side, and it used to be two
It
brown
could have
dwarfs
been, yeah. Would we see
Yes.
evidence of it? It's
Could
hard
very
to.
well be.
hidden
Yeah.
in plain sight.
Yeah.
Look at that. Like a
Yeah.
YouTuber that actually crossed over to regular entertainment.
What?
Okay. Anyway, sorry.
That's how the broad
So this is
spectrum
Atticus?
thing.
That was Atticus.
Atticus, thank you,
That's a
Atticus.
very good
Thompson. That was
question, yeah.
a great question.
And you know he's
Atticus.
building something in his basement.
You know, something I don't want anything to know about, but I'm sure the U.S. government does.
And the power grid dims every
Exactly.
once a week as he turns on his experiment. All right.
Okay, here we go. This is Jimmy Go Lightly. This is Holly's brother. It says, "Hi, this is James in Charlotte. How does the life?"
Wait, for those who were not alive in 1964.
Oh, it's still on the movie channel.
Is it? Okay.
The Turner Movie Classics. It's a great movie.
Yeah, so that was
What's her face?
Breakfast at Tiffany's.
Breakfast
Audrey
at Tiffany.
Hepburn.
Audrey
Yeah.
Hepburn.
Audrey
Thank
Hepburn.
you.
She was Holly Golightly.
Holly Golightly.
Based on the novel by
I have no
Truman
Truman
Capote.
Capote.
Yeah.
Yeah.
You didn't know that?
I did not know.
You're learning something every day here.
Let me tell you, that's why I come here.
Okay.
Because I'm stupid. All right. He says, "Hey, James in Charlotte here. How does the lifespan of a low mass star compare to the lifespan of other stars such as our sun?"
Yeah.
So,
The brown dwarfs are going to be around forever.
For a long,
That's what makes them
long
super
time.
useful. Yeah, the sun is going to stably fuse hydrogen for about 10 billion years, and we're about halfway through that. So if you want something to worry about, like the sun is about halfway through its lifetime. But the brown dwarfs, like we said, are going to last basically forever. For like our practical
Look at that.
definition of forever, which we use it in kind of a neat way, which is we call it galactic archaeology. Because some of the low mass stars that we can see now might have been around already since very early on. The high mass stars are going to have come and gone, but the low mass stars are going to be around. And one of the interesting things is that
Well, but you can make a low mass star today,
yes,
and it to be a low mass star, but some of the pool of low mass stars could have been born first.
Yeah.
right at the very beginning.
Right, and they're still
They're
alive.
still
you might
alive.
ask, how can we tell the
How are
difference?
you going to know the difference?
And we
or
can
is
tell
it degenerate?
Yeah, we can. This one we can tell the difference, and the answer lies in those high mass stars. because the high mass stars that have been fusing and then exploding have been creating heavier elements. And so the older a low mass star is, the longer ago it was formed, the fewer heavy elements it's going to have.
Okay.
And so the more recently formed low mass stars are going to have more of the heavy elements that were created in the subsequent generations of high mass stars, which is kind of cool if you think about it.
Get spectra and look at those elements.
Yeah, so you get the spectra, you look at the elements, and we have a special name for the low, we call it low metallicity, because we call this composition, how many heavy elements are in it, we call that metallicity. The low metallicity stars are called subdwarfs.
Oh.
Because they're under the main sequence of stars on this HR diagram.
Okay.
Yeah. It's a little bit weird, and they also tend to be blue in color.
Subdwarfs.
That's super cool, man.
They are fun to study.
Because they reveal themselves as their own population.
Yeah, subsolar
in the chart.
metallicity.
Got it. Okay.
Yeah.
Wow. Okay. All right. This is Matt Curtis. Matt says, hello, Doc Lord. Matt here, and Chuck is pronounced Matt. Boy, these people
Just in case.
These people are brutal today, man. They are brutal.
Chuck is pronounced Matt.
Coming from South Carolina here. Given that our space telescope technology is improving and we keep discovering more and more exoplanets, what will it take to directly capture an image of one of them? Deducing their existence through transit or gravity wobble is great, but what improvements would be required to show an image to the public directly?
Oh.
You want to see like oceans and continents.
So it depends.
He wants a travel brochure.
Yeah.
If you want to, so I like to call, because we do have images of exoplanets.
Right.
This is an amazing
Direct
thing.
imaging.
Direct images of exoplanets.
Nice.
It's
Well,
hard.
But how many pixels?
Yeah, a handful. And how many planets? It's like also 10 planets maybe or something like that. But one of them has stood the test of time. So this is also kind of back in my day of exoplanets. Back in 2008, 2 directly imaged exoplanets were announced. One was in around the star Fomalhaut, which famously had a disk, and it was a little like bright thing in the disk. And then there was
star
another.
is a southern hemisphere.
That's it's a pretty bright star though. It's got a name, like a star with a relatively normal name is a star that you can see in the night sky. And then the other one was HR 8799, which with a number like that you can't see it in the night sky. But it had 3 planets detected around it. And both of these, one was done with the Hubble Space Telescope, one was done with a ground-based telescope. But they're amazing discoveries. It's a handful of pixels and it's really fuzzy images. It's like, but the Fomalhaut one actually seems to have been a spurious discovery. Like it's just a clump in the disk that kind of didn't move the way it was expected to move and has since gone away. The HR 8799 system, they found another planet even closer in. So there's 4 planets in the system, and you can, over the time, put the images together and watch the planet's orbit.
Oh, wow.
It's beautiful. And so somebody, Jason Wang, I believe his name is, has made GIFs that every once in a while go around social media of like a little animation of the images where we can watch planets orbit around a star other than the sun, which I think is just amazingly...
it's crazy. I love it.
Yeah.
Think about it.
We haven't found that many more.
But years to go around its host star.
Right.
You need data over that entire
decades,
time.
yeah, basically.
To really get the good.
Yeah, and this is the HR 8799 system is like a souped up solar system. Mm-hmm. It's a bigger star than the sun. The planets are bigger. They're like 5 to 10 times the mass of Jupiter, and they're all further out than our
so it's
gas
bigger
giant
and brighter.
planets,
So
but similar to it.
That's cool, man.
Time for one more question.
All right. Okay, so since we're on exoplanets, let's do Paula Patsova, who says, hello, Dr. Rice, Dr. Tyson, Lord Nice. Paula here from Slovakia. What is the potential of habitability of orbiting planets around a brown dwarf or low-mass stars?
Yeah.
Ooh, good one.
Yeah,
good
especially
one.
the low-mass star. Like the brown dwarfs, maybe, but they're kind of the extension of the low-mass stars. But the low-mass stars, like they might actually be better targets for finding Earth. I don't want to say Earth-like, but I'll say Earth-size planets at the very least. Because for these indirect methods that were mentioned earlier, the indirect methods, it's easier to see small planets relative to small stars. It's easier to see planets close into the stars.
Right.
And so both of those mean that if you look around a small star, it's easier to find Earth-size planets and kind of Earth-temperature planets.
Okay.
So because those are going to be closer into the star because it's a cooler star. So it's like a smaller fire.
I mean, if you're going to have an Earth temperature,
right?
Yeah.
and it's way dimmer or way less luminous than our sun, you got to be way closer.
You can be closer
to get that same temperature.
Yeah, to get that same equilibrium temperature. But then it's easier to find that planet with these indirect methods that we use most of the time. And so now these small stars have been like really intriguing targets for searching for exoplanets.
Right.
And so the TRAPPIST-1 system is a very famous system that was discovered a handful of years ago with 7 Earth-sized planets in orbit around that star. And like something like 3 or 4 of them
TRAPPIST
are
is the name of the
solidly,
star.
yeah, this one, well, weirdly enough, the star was known before. TRAPPIST is actually the acronym for the survey.
Oh, okay, the catalog.
Transiting, blah, 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 blah. But it's a Belgium, the group includes Belgium Observatory.
Okay.
And so it's like, we call it a backronym sometimes, where they think of the clever term that they want, and then they make up the acronym to go with it.
A backronym, I love it.
Yeah, a backronym. Yeah, that's a fun portmanteau. So the TRAPPIST-1 system is super great because a solid 3 or 4 of those planets could be in the habitable zone.
Right.
Around. So the habitable zone is where it's the right temperature for liquid water.
Goldilocks zone.
Yeah, Goldilocks zone. But it doesn't tell you anything about the atmosphere, which you would also need to have liquid water on the surface. And so there's still a lot of unknowns, a lot of what ifs for those. But the low mass stars are really exciting targets for Earth-size exoplanets, at least.
Wow. Cool. Exciting.
Yeah.
All right.
Yeah, that's great.
Well, Emily, thank you. You don't
Thanks
come on
for
here
having
often
me.
enough. We got to bring.
I'm around.
We'll just reach
She's
out.
like, I'm right upstairs.
No, just upstairs.
Yeah.
Walking by.
Call me. Well, thank you for bringing back your expertise on this zone of ignorance that existed for so long that finally people are jumping in.
Yeah.
Getting their hands dirty.
Yeah.
We've always kind of wondered, right?
Yeah.
But now we know for sure, which is amazing.
Very
A lot of
cool.
the things.
All right.
Good stuff.
All right. Well, let me take us out with some reflections on this moment. In my field, astrophysics, many of us confront people who ask the very sensible question, why are we spending money on anything you're doing when we have all these problems here on Earth? And okay, before we did all of this, did you not have those problems on Earth? I think you had them long before any of us spent a dime of tax money or any other money trying to understand the universe. What we do know is what we discover expands our view, not only of the world, but of our place within it. And when I was growing up, there were planets and there were stars. And no one really thought much about, well, how do you get between one and the other in the universe? What does the universe say about that? And then we learned there's an entire field that we didn't even know would exist or could exist and now does exist that specializes in the transition between what you are as a planet and what you would become as a star. This is more about our world, our universe, our home. And it could be that this will help us discover life on a planet around a star sometime in our future. And so whether or not that specifically puts food on your table, I'll ask you a little differently. I'll say, how much is the universe worth to you? And that's the cosmic perspective. Neil deGrasse Tyson here for StarTalk Cosmic Queries. As always, keep looking up.